Okay, so I have decided to make these videos topic by topic since making a very long video it might be difficult for you to download and view at one time. So the first topic that we will discuss today is rotational kinematics. Now you will remember we talked about kinematics for one-dimensional motion and two-dimensional motion, and basically it's the study of the motion itself with no regard to the cause of the motion. So that was the study of kinematics. Now we're going to adapt this to the rotation motion, and for this we're going to consider a point P on a disk. So let's have a disk here that is rotating in this direction, so it's in the counterclockwise direction, and let's have this point located at a radial distance r from the origin. So that's the center of the disk. So here I have this point P that is moving together with the disk, and let's call the radius of this disk capital R. All right, and now if this disk has moved through an angle theta, let's say, so I define this angle theta with respect to the positive x-axis as my reference, I see that it goes through an arc length of S. Okay, so I notice that there is a point P on a rotating disk, and I'm looking at its position at a certain time. So let's say that this rotation started at t is equal to 0. This point P was right on the x-axis, and now it has rotated through an angle theta, and it draws an arc length of S. Okay, so at a certain time t, I find that the disk has rotated through an angle, rotation angle is theta, that is defined with respect to the positive x direction, and P moves through an arc length of S. Okay, now as you remember, the circumference of this circle is 2 pi r. So if you rotate through an angle theta, the arc length that we're going to draw, S, is going to be equal to r times theta. So this actually you can use as the definition of the angle. So theta from this expression you can see is so theta is equal to S divided by R. So I have two lengths here, therefore the dimensions cancel. So I find that angle is a dimensionless quantity. Dimensionless quantity. Okay, so how do we measure the angle? Well, it has an artificial unit we give to the angle is radians. Radians, so we have the abbreviation rad for radians. Okay. And you know we can also measure the angle in degrees. And how do we convert between the two? If the angle is given in degrees, if you divide it by 180 and multiply it by pi, you're going to get the angle in radians. All right. Now we call theta is the angular position of point P. So small r would be the radial position of point P. So we're using polar coordinates basically to describe this rotation. Okay, so let's say that this point has moved from an angular position theta initial, radial position r, which is point A, to another point in space at t final, time is equal to t final, radial position theta final, radial position r, angular position theta final at point B. Okay. Now we can define the angular displacement. So if theta I is initial angle, initial angular position, and theta f is the final angular position, we can define the change in the angle delta theta, theta final minus theta initial, as angular displacement. Okay, so that's the change in the angle. Now, since the angle is changing in time, we can talk about an average angular speed. So this is how we define it. The average angular speed, so I call this omega average. Omega average is theta final minus theta initial divided by t final minus t initial, or in other words, it's the change in angle, angular displacement, divided by the change in time, the period of time it takes to achieve this angular displacement. And what is the unit here? This is going to be in radians per second. Dimension wise, this is just 1 over time. So remember, angle is a dimensionless quantity. Okay, so that's the definition of average angular speed. Now, similar to translational kinematics, we can talk about instantaneous angular speed. So the speed with which it rotates may be changing in time. So that would be the limit as delta t goes to 0, delta theta over delta t, which is by definition the derivative d theta dt, that's also in radians per second. Now, I have been talking about these magnitudes basically of angular, so that's the speed, so it's the magnitude. So I realized that this number that I will get from such a calculation would be positive if the rotation is counterclockwise, because that's where I defined angles to be positive. So this is the positive angle direction. And if omega is, if it's a clockwise rotation, omega would be negative. The angle would be decreasing in time. Okay. Now, similar to translational kinematics, again, we can extend this discussion to acceleration. I can talk about average angular acceleration. That would be omega final minus omega initial divided by t final minus t initial, change in angular speed divided by the time interval it takes to achieve this. So what would be the unit of this one? That is radians per second square, our artificial unit radians divided by second square. Dimension wise, it's 1 over time square. And similarly, we can define the instantaneous angular acceleration alpha and this would be equal to the limit as the time interval goes to 0, change in angular speed divided by the time interval. It is the derivative d omega dt in radians per second square again. So that would be my instantaneous acceleration. Now, actually, we can define these as vectors, so I can have an angular velocity and angular acceleration. And the way we define it, so the vector nature of this comes from or can be found using the right-hand rule. So you can see here, if you have the disk rotating in the counterclockwise direction, you put your right hand, you curl your fingers around the center, a rod that goes through the center, let's say, your thumb will point towards the direction of the angular velocity. And you can see if it rotates in the clockwise direction for negative angular speed, you will have an angular velocity pointing in the opposite direction, which is also found using your right-hand rule. So as a vector, the angular acceleration is the rate of change of angular velocity d omega dt. So if you have a positive angular acceleration and you find that this angular acceleration is parallel to your positive angular velocity, what does that mean? That means the angular velocity is increasing in time. If you have angular acceleration opposite in direction to your instantaneous angular velocity, that means omega is decreasing in time. So as you can see, for this rotation there is only one axis on which the angular velocity and angular acceleration can point, and that axis is the rotation axis. So it's either positive or negative. So the vector nature of these quantities are embedded in the sign of the or can be shown with the sign of the angular speed as well. So you can take care of the vector nature using the sign. All right, now we actually know quite a lot about these the translational kinematics. So since we see a one-to-one correspondence between rotations and translations, we can associate the angular position theta with the position x, the angular velocity omega with the velocity v, and angular acceleration alpha with the translational acceleration a. And by doing so, we can basically find the corresponding rotational kinematics equations for all kinds of motion. For example, for constant alpha, constant angular acceleration motion, I can say that if alpha is a constant, I should have omega as a function of t is initial value of omega plus alpha t, and the angular position as a function of time would be the initial angular position plus omega I t plus 1 over 2 alpha t square. So basically, remember, this is integral alpha dt, this is integral omega dt from t is equal to 0 to time t. So these are the same in translations. You remember, we have the initial position plus v initial t plus 1 over 2 at squared. Now, if I have a non-uniform rotation where there is an angular acceleration involved, then I can go back to our previous discussion for uniform circular motion. Remember, from our previous discussion on circular motion, we said that using the polar coordinates, when you have a point rotating through an angle theta here, this is your radial position r. Remember that we have defined a unit vector theta hat pointing in this direction and r hat pointing in the radial direction. And what we said was that r hat is cosine theta I hat plus sine theta j hat. So those are the unit vectors in the Cartesian axes, I hat and j hat. So that's my x-axis, that's my y-axis. And theta hat, remember, is minus sine theta I hat plus cosine theta j hat. So this angle this vector makes with the vertical is theta. Okay, so that's from our previous discussion. Now, the radial position vector r is r hat, and if I take one derivative, I get the velocity that is the time derivative r dot r hat plus r hat dot, and the acceleration would be given by dv dt as well. So for these calculations, I have to remember what is r hat dot and what is theta hat dot, so the rate of change of these unit vectors. So this one is dr hat dt, it is theta dot theta hat, and this is d theta hat dt, it is minus theta dot r hat. Okay, I'm not going through these calculations in detail since we have done it before many times. Okay, now using these derivatives, I find that the velocity vector is, if there is no change in the radial position, let's say r dot is 0, then this would be r hat dot r theta dot theta hat, which is by definition angular speed, omega r in theta hat direction. So the speed of the rotation is omega r, and the acceleration would be omega dot r theta hat omega r dot theta hat plus omega r theta hat dot. Now, if the radial position is not changing. This is 0. This would be now angular acceleration alpha r theta hat minus omega square r hat. So now I have a tangential acceleration of alpha r and a radial acceleration of omega square r. But written as a vector, remember that in the total acceleration I have a minus sign because the centripetal acceleration is always pointing towards the center. And also you can see that this tangential acceleration from our discussion of non-uniform circular motion is actually dv dt. So we have v is equal to omega r. If you take a derivative with no change in radial position, you would get alpha r as the answer for tangential acceleration. Okay, so let's look at a few examples here to make it more clear. During a certain time interval, the angular position of a swinging door is described by theta is equal to 5 plus 10t plus 2t square, where theta is given in radians and t is in seconds. Determine the angular position, angular speed, and angular acceleration of the door at different times, at t is equal to 0 and at t is equal to 3 seconds. Okay, first let's find as a function of time what is the angular speed. Omega is d theta dt, so I take one time derivative. I'm going to get 10 plus 4t in radians per second. And for angular acceleration, I have to take one more derivative, the omega dt, or second derivative of theta angular position with respect to time. That would give me 4 in units of radians per second square. Now to answer part A, is basically asking me at t is equal to 0, what are these quantities? Well, theta at t is equal to 0, as you can see, is 5 radians. The angular speed omega at t is equal to 0 is 10 radians per second, and angular acceleration alpha at t is equal to 0 and for all times is 4 radians per second squared. This is actually a constant angular acceleration motion. So for part B, I want to know what happens at t is equal to 3 seconds. So I substitute t is equal to 3, 5 plus 30 plus 9 times 2, 18. I get 53 radians. For angular speed at t is equal to 3 seconds, I get 10 plus 4 times 3, 12, 22 radians per second. And for angular acceleration, alpha at t is equal to 3, remember it was a constant, 4 radians per second square. So basically, these would be the answers to this problem. Okay, so let's move on to another example. A bar on a hinge starts from rest and rotates with an angular acceleration. Alpha is 10 plus 16. So this is not a constant alpha motion now. Alpha is time dependent, where alpha is in radians per second square and t is in seconds. Determine the angle in radians through which the bar turns in the first 4 seconds. Okay, so I want to go from alpha, the angular acceleration, to the angular displacement. So I have alpha is equal to 10 plus 6t, which is d omega dt. So omega as a function of time would be alpha dt from t is equal to 0 to time t. So this would be 10t plus 3t squared when I take this integral, plus omega initial, but omega initial is 0 radians per second. How do I know this? That's here. The hinge starts from rest. Okay, so I have to keep omega initial 0. So this doesn't exist. Now the angle as a function of time will be given by integral from 0 to t omega dt. So I take another integral. This will give me 5t squared plus t cubed plus theta initial. Now I can say that theta initial was 0 because it's not specified exactly what theta initial is, or you can say that this is delta theta, the total angle through which it turns in this time interval, 5t squared plus t cubed in radians. Now how much is the total angular displacement? 5 times 16 plus 64. So the answer would be 144 radians. So that's the total angle through which it turns in a time interval of 4 seconds. Okay, so let's move on to another example. A car traveling on a flat, unbanked circular track accelerates uniformly from rest with a tangential acceleration of a. The car makes it 1/4 of the way around the circle before it skids off the track. From these data, determine the coefficient of static friction between the car and the track. Now this car is going through an angle of 90 degrees, and then it basically skids off the track. So I have a total angular displacement of pi over 2 radians, okay, before it skids off the track. So for non-uniform circular motion where I have a tangential acceleration and a radial acceleration, I have to remember that the tangential acceleration part is alpha r and it is dv dt, where v is equal to omega r for rotational motion. Okay, so I find that alpha, and this is given as a, the tangential acceleration, alpha is a over r. So that's my d omega dt. So that means if I take one integral from this one, omega will be, as a function of time, a over r t plus omega initial, but then I go back to the problem statement, it says from rest. So it's a uniform acceleration from rest, so omega initial was 0. Okay, now what is the angular displacement delta theta? It is integral from 0 to t omega dt, so that would be a over r 2r t squared plus this, since I said delta theta, this is already including the initial angle. So what is the information given to me? The angular displacement I have is pi over 2 before it skids off the track, so that's a over 2r t squared. So I find that this is going to happen when t is equal to r pi over a square root. So at this time, it's going to skid off the track. All right. And since this is the critical point at which it skids off the track, I know that the static friction will have reached its maximum value, which is mu s times the normal force. So if the car has a mass m, let's call m mass of the car. Hopefully this will disappear in my answer because there is no m in the question statement. So this would be equal to mu s times mg. How do I know it's mu s times mg? Because it's a flat track. It's not banked. So if you remember, if it's banked, I have to consider the component of mg that is perpendicular to the track. Okay, so now I don't have to worry about this. So this is going to be equal to mass times acceleration, total acceleration of the car when it skids off the track. So the total acceleration of the car has to be mu s times g when it skids off the track. Now there is another component of this acceleration, which is the centripetal part or the radial part. Remember, this is v square over r or omega square r. So I want to know what is the centripetal acceleration at time t. So this is equal to a square over r square t square times r. And when t is equal to square root r pi over a, let's find what this is. A square over r square, r pi over a times r. So I find that this centripetal acceleration, this one will get rid of these two, this one will get rid of this two, is equal to a times pi. Okay, so at time t, I find that I have a total acceleration a, which is a theta hat minus a pi r hat. So I have a tangential and radial component here. So the total acceleration has to be square root of a square plus a square pi square. So it will be a square root 1 plus pi square. Now, since I find that the total acceleration has to be mu s times g, this is going to tell me what mu s is. Mu s is a over g square root 1 plus pi squared. So I have found the coefficient of static friction for this surface between the car and the track. Okay, so let's look at one more example. A shaft is turning at angular speed omega at time t is equal to 0. Thereafter, its acceleration is given by alpha is equal to a plus bt. So omega initial is omega at time t is equal to 0, and alpha angular acceleration is a plus bt. So I want to know the angular speed of the shaft at time t. This is d omega dt. So I find that omega as a function of time will be the integral from 0 to t alpha dt. It will be a t plus b t squared over 2 plus omega initial. That's the value of omega at t is equal to 0. So that's my first answer. So that's the answer to part A. This is part A. Now in part B, it asks me through what angle does it turn between t is equal to 0 and t is equal to t. The angular displacement is integral from 0 to t omega dt. So I have to take one more integral here. So this will be a t squared over 2 b t cubed over 6 plus omega initial was omega t. So that's the total change in angle. So between t is equal to 0 and t is equal to t, I have this angular displacement for the shaft. And one last example. As a result of friction, the angular speed of a wheel changes with time according to d theta dt is equal to omega 0 e to the minus sigma t, where omega 0 and sigma are constants. So omega as a, sorry about this, omega as a function of t is given by omega 0 e to the minus sigma t in radians per second, I'm assuming. Yes. The angular speed changes from 3.5 radians per second at t is equal to 0. So omega at t is equal to 0 is 3.5 radians per second to 2 radians per second at time 9.3 seconds. So omega is 2 radians per second at time 9.3 seconds. Use this information to determine the constants sigma and omega 0. So that's the first task. Now omega 0 is omega 0 times e to the 0, that's omega 0, 3.5 radians per second. And omega at t is equal to 9.3 is going to be equal to 3.5 times e to the minus sigma 9.3. So this has to be equal to 2. So I have minus 9.3 sigma is equal to natural logarithm of 2 over 3.5. So sigma is 1 over 9.3 natural logarithm 3.5 over 2. I operated the minus sign by inverting the fraction, the ratio from 2 over 3.5 to 3.5 over 2. So from this, I can calculate sigma. It is 6.02 10 to minus 2. And what is the unit of sigma? Because it's sigma times t has to be dimensionless. It's 1 over second. So this is omega 0 and this is sigma. Okay, now part B. Determine the magnitude of the angular acceleration at t is equal to 3 seconds. Now angular acceleration alpha is d omega dt. So I take one derivative. I get minus sigma omega 0 e to the minus sigma t in radians per second square. So I substitute for time t, what is the value of alpha? Minus 6.02 10 to minus 2 times 3.5 e to the minus 6.02 10 to minus 2 times 3. So I can calculate this. It turns out to be minus 0.176 radians per second square. Part C, the number of revolutions it makes in the first 2.5 seconds. Well, for that, I have to know the angular displacement, delta theta. The angular displacement is the integral omega dt from 0 to t. So that would be minus omega 0 over sigma e to the minus sigma t. So the integral of omega. So that's the change in the angle to total angular displacement between time 0 and t. And this is going to be, as you can see, there will be a contribution from t is equal to 0 here. So it's minus omega 0 over sigma e to the minus sigma t minus 1. Okay. So I can substitute for the total angular displacement at a time interval of 2.5 here. So it's going to be minus omega 0 over sigma 6.02 10 to minus 2 e to the minus 6.02 10 to the minus 2 times 2.5 minus 1. So this gives me an answer 8.12 radians. But the question is really how many revolutions? So one revolution is 2 pi radians. So the number of revolutions will be 8.12 divided by 2 pi. That is 1.29 revolutions. Okay, so to answer part C, let me open up some space here. It's part D, sorry. What is the total number of revolutions before it comes to rest? So when does it come to rest here? So omega as a function of t is omega 0 e to the minus sigma t, and as t goes to infinity, omega goes to 0. So the total angular displacement when t is equal to infinity or t goes to infinity will be the total number of revolutions it makes before it comes to rest. So if I substitute t is equal to infinite in the delta theta expression, I will have minus omega 0 over sigma e to the minus infinity minus 1. So I will have as the answer omega 0 divided by sigma. So what is omega 0 divided by sigma? If you substitute delta theta at t is equal to infinity, is 3.5 divided by 6.02 10 to minus 2. The total displacement is 58.2 radians. Again, since it asks you how many revolutions this corresponds to, you have to divide it by 2 pi here. So 58.2 divided by 2 pi gives me 9.26 revolutions as the answer. Okay, so that completes our discussion of rotational kinematics. In the next video, I'm going to discuss rotational kinetic energy and moment of inertia calculus.